Let's look now at two different paths that work could follow on an ideal gas between the same initial and final states. So here's what we'll call path 1. At the start of path 1, the pressure exerted by the weight and the piston is much greater than the gas pressure. So the downward green vector is much longer than the blue P gas vector to indicate that. Compression is immediate and rapid because of this pressure difference, and the external pressure remains constant throughout. Notice that the length of the green vector does not change throughout this process. So we start at an external pressure that is at a certain level, and the external pressure remains constant throughout. And V1 is larger than V2, so we start out in the upper right of the state space graph that you see on the right-hand side of the slide. As the process occurs, the volume of the system decreases, but the external pressure remains constant, and so we move from right to left as the process takes place. The process stops when the external pressure is perfectly counterbalanced by the gas pressure. We know from the ideal gas law that the gas pressure will increase as compression takes place. This is what we'll call path 1, immediate and rapid compression due to a finite and large difference between the external pressure and the gas pressure. We can do this same process in a slightly different way. So imagine we started with a pile of sand with the same mass as that mass M that we had in path 1. Rapidly and immediately we remove some of that sand so that the external pressure equals the gas pressure. So in the very first state at the far left, the external pressure is greater than the gas pressure. But imagine we're holding up the piston with a couple of pins, for example. We remove a portion of the sand to immediately and rapidly decrease the external pressure down to the point at the bottom right of the state space graph. And at this point, the two pressures, external and gas, are in equilibrium. Now we add individual grains of sand back on top of the piston, increasing the external pressure ever so slightly and decreasing the volume ever so slightly, allowing the system and the surroundings to equilibrate between addition of these grains of sand. We stop when the volume reaches V2. Notice that we've moved between the same 2 points in state space. That starting external pressure and the final external pressure are the same. It's just that the way we did it was different in path 2, using grains of sand instead of a large mass M. If we compare these two graphs, we'll notice that the work for the two different paths is different. Work is the area under the curve, expressing the relationship between external pressure and the system volume. And that's what's highlighted in green on these two state space graphs for paths 1 and 2. The definition of work is here in the upper right of the slide, and it shows us that work is the area under the curve. Work is an integral. Clearly, the areas of the two shaded regions are different. The work in the case of path 1 is much larger than the work in the case of path 2, even though we're moving between the same initial and final states. Much less work was performed when we used grains of sand instead of adding the mass M all at once. Work is path dependent. This is proof positive of that. We're going to revisit these two paths multiple times in our study of thermodynamics because they illustrate two different general types of processes, reversible and irreversible, that are very relevant to chemical thermodynamics. So keep these two paths in mind, and especially at this point, notice that the work performed depends on the path we use to get between two different points in state space.